Hello everybody! In this video, we'll learn about two new concepts in matrix algebra called eigenvalues and eigenvectors. They're special constants and vectors associated with a matrix that arise in context with this observation, that sometimes matrix multiplication is equivalent to scalar multiplication. Let me show you an example of what that means. Let's say you have this matrix, 3, -2, 1, 0, and you multiply it by the vector 2, 1. Well, if you calculate this matrix vector product, the result is 4, 2. However, 4, 2 is also equal to 2 times the original vector, 2 times 2, 1. So in this case, multiplying this vector by this matrix is the same thing as multiplying this vector by a constant. Now, this is certainly not always the case. In fact, it's usually not the case. For example, if I multiply this matrix times the vector 1, 3, the result is the vector -3, 1, and -3, 1 is not equal to any constant times 1, 3, no matter what constant you use here. Now, mathematical tradition is that for this constant, we'll use the Greek letter lambda. So our goal is to investigate this question. Right? Sometimes matrix multiplication looks like scalar multiplication. Well, in which cases does it work out like that? In other words, given a matrix, capital A, find constants lambda and vectors v such that this equation is true. Matrix A times vector v is equal to the constant lambda times the vector v. And when this equation is true, the values, lambda for which it's true, those values are called eigenvalues of your matrix A. And the vectors for which this is true, those vectors v, are called eigenvectors of your matrix A. So it's an interesting question, but it's also very useful for applications, as we'll see in following videos. But first deal is, let's try to figure out how to solve this equation. So how do we find these eigenvalues lambda and these eigenvectors v? Well, let's start out with the one thing we know. We want them to satisfy this equation. The first thing we'll do is on the right-hand side, we'll rewrite lambda times v as lambda times the identity matrix times v. Now, we can always multiply by an identity matrix if we wish, because multiplying by the identity matrix does not change the value of anything. It's like multiplying a number by the constant 1. The reason we want to do this is the next step will be to take this value on the right-hand side and move it over to the left. So we'll subtract this value from both sides. So on the left-hand side, we'll have a times vector v minus lambda times I times the vector v. And on the right-hand side, well, we have nothing left, but we have to write something. What we have left is the 0 vector, right? Both sides of this equation, the results are vectors. So if we move everything over to one side, on the remaining side we have a vector consisting of only zeros, which we'll typically write as this. Now on the left-hand side, both of these terms have a v in it. So we can actually factor out multiplication by the vector v. And so now we have this computation, matrix A minus lambda times the identity matrix I. Right, the result here will be a matrix. That matrix times the vector v equals the 0 vector. This matrix that we're multiplying by vector v, we'll call that matrix M. So let M equal A minus lambda times I. we can rewrite this equation more succinctly as m times v equals 0. Now, what do we know about m? Not a whole lot yet, but we have talked a lot about determinants recently. And we know that if the determinant of a matrix is not 0, then the inverse matrix exists, and we could use that matrix to solve for v. In this case, we would multiply both sides of this equation by m inverse, and what we'd be left with is vector v equals m inverse times the vector of all zeros. But if you multiply anything times a vector of all zeros, right, that matrix vector product, that's going to give you a vector of all zeros. And that would be the only solution in this case. And certainly that's true, right? If we look back at our original equation, if you take a matrix times a vector of zeros, that's going to be equal to a constant times a vector of zeros. It's going to be equal to 0 times a vector of zeros. But that's not very interesting, right? It's always true, but we're looking for non-zero solutions. Sometimes this solution is called the trivial solution, because it's always true. We know that without knowing anything about A. And we're really interested in finding the other solutions, the so-called non-trivial solutions. So in this case, we'll actually be really interested in the case where the determinant is equal to 0. Right? The reason we're interested in that is that if the determinant is equal to 0, that tells us m inverse does not exist, and that metaphorically opens a door to non-trivial solutions, to additional solutions. Now, just because m inverse does not exist, that doesn't mean that there's necessarily no solutions. If m inverse doesn't exist, there are two possible cases. Right? As we've seen when we try to solve linear equations, there's either one solution, no solutions, or infinitely many solutions. And I like to remember this by making an analogy with standard algebra. Right? Something like the equation 0 times x equals 1. Right? This 0 does not have an inverse, and this equation has no solutions. But in this equation down here, 0 times x equals 0, this 0 does not have an inverse, but there are infinitely many solutions. Right? We're very interested in this case right here. Can we identify infinitely many solutions for v and the corresponding lambdas? Right, so we'd like to focus our attention on this possible case, right, when this matrix M has determinant 0. So from the previous slide, I'm just copying over some of that. We started out with the equation A times V equals lambda times V. We rewrote that to get the equation M times V equals 0. Where M was defined to be A minus lambda times the identity matrix. Now we'll just focus our attention on 2 by 2 matrices here. If A is a 2 by 2 matrix, so A could be the matrix little a, b, c, and d, then M would be this matrix minus lambda times the identity matrix. Well, lambda times this matrix gives you the matrix lambda 0, 0, lambda. And then we want to subtract this matrix from the matrix A. So we get A minus lambda, B minus 0, C minus 0, and D minus lambda. Now we're interested in the non-trivial case to get some non-zero solutions. So we want to force the determinant of this matrix to be 0. Right? So we'll calculate the determinant of this matrix. Right? It's this A minus lambda times D minus lambda minus C times B. And we're interested in when this is equal to 0. Now multiply this out and group all the lambda terms, And what we have here is actually a quadratic equation. In this case, A, B, C, and D are going to be constants in some given matrix, and lambda is the unknown. Lambda is the variable we would like to solve for. In quadratic equations, we know how to solve those. This equation is sometimes called the characteristic polynomial of this matrix. And we can actually solve this equation for lambda. That tells us what the eigenvalues of the matrix are. And once we know the eigenvalues, we can plug those in to solve this equation. So again, A, B, C, and D are given. Once we know what lambda is, we have this equation which we can solve for x and y. Right? That tells us V, that tells us the eigenvectors. Now, it's time to do some examples. Let's say we want to find the eigenvalues and eigenvectors of this matrix. A is the matrix 5, 2, 3, 6. And of course, we always like to check our work. So once we find them, we also want to verify that A times V is equal to lambda times V. In general, when we solve a quadratic equation, we'll get one or two solutions, usually two. Okay, so first we'll define the matrix M. So M is always A minus lambda times I. So that's 5, 2, 3, 6 minus lambda times I. That's lambda 0, 0 lambda. When we do the subtraction, we get the matrix 5 minus lambda, 2, 3, and 6 minus lambda. Once we have that, we want to find the determinant and set it equal to 0 and solve for lambda. Right, so we're coming up with a characteristic polynomial. So the determinant of this matrix is 5 minus lambda times 6 minus lambda minus 3 times 2. If we FOIL this out, we'll get 30 minus 6 lambda minus 5 lambda plus lambda squared minus 6. Then grouping those terms, we have lambda squared minus 11 lambda plus 24, and we'll set that equal to 0. Fortunately, this factors very nicely. This factors into lambda minus 8 times lambda minus 3 equals 0. So we can solve for lambda. Either lambda equals 8 or lambda equals 3. In this case, these are the two eigenvalues of this matrix. And for each one of these, we'll find a corresponding eigenvector. As it turns out, there are going to be infinitely many solutions for each eigenvector. We just need to pick one of them that works. So let's start with lambda equals 8. Remember the matrix M? That was 5 minus lambda, 2, 3, and 6 minus lambda. So we can substitute lambda equals 8 in for each one of these lambdas. And then we calculate and we get this matrix. Negative 3, 2, 3, negative 2. And we want to solve the equation M times V equals 0. So here's our matrix M times the vector V. We'll put some variables in here. That's equal to the 0 vector, the vector of all zeros. We can convert this into a system of equations again. That makes it a little bit easier to figure out what x and y will be. And you might notice that if you take the first equation and multiply it by negative 1, you're going to get the second equation. Right? The system of equations is redundant, and that will always be the case. Right? There's always going to be a free variable because there's always going to be infinitely many solutions. So we can pick a value for x, and we'll choose one that makes it easy to solve for y. Right? For example, we could pick x equals 1, but if x equals 1, then y is going to be a fraction, and I prefer to avoid that. And we also do want to avoid the solution 0, 0. That's a trivial solution and that doesn't tell us much. But in this case, one easy solution to C, relatively easy, would be x equals 2 and y equals 3. In that case, these equations are true, so we'll choose that solution. And there are other solutions. In fact, any multiple of these solutions would be another solution. But in this case, this is an eigenvector. V equals 2, 3 is an eigenvector for this eigenvalue, lambda equals 8. To check this equation, well, it's just a matter of multiplying the original matrix, not M, but the original matrix A times the vector V, and here we get 16 and 24. And then we'll do scalar multiplication, 8 times 2, 3, and again, we get 16, 24. So we get the same result. So yes, the matrix multiplication is the same as the scalar multiplication in this case. There's one more eigenvalue we can investigate here. We also found that lambda equals 3 is of interest. So again, starting with the matrix M, plug the eigenvalue lambda equals 3 in here and in here. When you subtract, you'll get 2, 2, 3, 3. And we need to solve the equation M times vector V equals a 0 vector. So we'll write that out with x's and y's for our vector V, convert it to a system, and in this case we can use 1 and negative 1 as a particularly nice solution for x and y. So our chosen eigenvector is 1, negative 1. That is an eigenvector for the eigenvalue lambda equals 3. Right, this wouldn't work for lambda equals 8. This is dependent on this eigenvalue. And checking, again we multiply the original matrix A times our eigenvector. In this case we get 3, negative 3. And then we do the scalar multiplication with this eigenvalue, and we get the same result. So we're confident that this solution is also correct. We'll do one more example. So let's say we want to find the eigenvalues lambda and the eigenvectors v of this matrix, negative 4, 2, 3, 1. And as always, we like to check our work. We'll check that A times V equals lambda times V. So the procedure is exactly the same. We write down our matrix M. It's A minus lambda times I. And so this will be negative 4 minus lambda, 2, 3, and 1 minus lambda. We want to calculate the characteristic polynomial, so we find the determinant of this matrix, so negative 4 minus lambda times 1 minus lambda minus 3 times 2. And again, we expand that out and set it equal to 0, and conveniently it factors again. In this case, we'll get lambda plus 5 times lambda minus 2 equals 0, which tells us our eigenvalues are lambda equals minus 5 and lambda equals 2. And for each of these, we want to find the corresponding eigenvector. So we'll start with lambda equals 2. In this case, substitute 2 into your matrix M. Here we get negative 6, 2, 3, negative 1. Then we solve the equation M times V equals 0. And again, we notice that there's a free variable. There should always be a free variable. In this case, the second equation is negative 2 times the first equation. So we could choose x equals 1 and y equals 3. That gives us a solution to these two equations, and there's our eigenvector. V is the vector 1, 3. And that's an eigenvector for the eigenvalue lambda equals 2. To check is straightforward. Calculate the matrix vector product. We get 2, 6. Calculate the scalar multiplication. We get the same result, 2, 6. So that checks out. There are two eigenvalues. We still have lambda equals negative 5. As before, plug in -5 here. We'll get the matrix 1, 2, 3, 6. Set up your equation, m times v equals 0. Writing that as a system, I see that we could choose x equals 2 and y equals -1 as a solution. So, our eigenvector, there are many correct eigenvectors, but the one we've chosen here is 2, -1. That's our eigenvector for the eigenvalue, -5. To check, calculate the matrix vector product, we get -10, 5. Calculate the scalar multiplication, we get the same result. So this checks out. So that tells us how to calculate eigenvectors and eigenvalues. It's kind of inherently interesting that sometimes matrix multiplication happens to align with scalar multiplication. But as we'll see, this actually helps us perform related matrix calculations, which we'll see in future videos. For now, it's time to learn math by doing math. And so here's an exercise you can work on. Find the eigenvalues lambda and the eigenvectors v of this matrix. -1, 4, 6, 9. And you should find 2. It should factor nicely. And once you've figured out those eigenvalues, for each one, find the associated eigenvector and check that this equation works. All right, that's it for this video. Good luck with this exercise, and thanks for watching.